Hello everyone. Today we will be starting my series where I learn some mathematics on my own, and I'm just going to record myself doing so. So if you want to follow along, you can. Uh, I will be doing this just to one, educate myself, and two, just to allow you guys to follow along while I do. Uh, on this YouTube channel, we will start having actual classes where we already know the content, and we will be delivering basically our knowledge in the form of whatever style of video we choose. However, for today, I'm just going to, and this series, I'm just going to be trying to learn this on my own, and I'll explain my thought process. So the first thing we will be doing today will be permutations and combinations. I already know some uh, parts of this lesson due to learning it before. However, I'm still not very confident in basically what's the field of combinations and permutations. So definition 1.1.1 states that a factorial is the product of all positive integers less than or equal to a given positive integer. In other words, n factorial equals to n times n minus 1 times n minus 2 and so on until 1. I'd assume this is pretty standard, though I assume there are ways to get the factorial of non-integers, but I guess we can stick with this definition for now. So the number of ways arranging n objects in a line is n. This makes sense. For the first place in the line, there are 4 possible things that can go there. So after 1 goes there, let's say it's just this one that goes there. There's only 3 left, and then so on. And then it's just 4 multiplied by 3 multiplied by 2 multiplied by 1. So the number of ways arranging n objects in a circle where rotations of the same arrangement aren't considered distinct is n minus 1 factorial. Now, I'm not really sure for this one. I've never actually explored this before, so I'm going to try to figure out what this means. So, where rotations of the same arrangement aren't considered distinct, so distinct means that they're different. So, if I have A, B, C, D, E, so if A is here, B is here, C is here, D is here, and E is here, this is a rotation where everything is moved one way clockwise. So these are not considered distinct. So these are the same as these. So obviously in this situation there are 5 factorial ways to place these balls into this circular circle. We can have 5, 4, 3, 2, 1. But n minus 1. That means we're doing 4 times 3 times 2 times 1. So we have to find a way to take this 5 out. So I guess oh yes, so you can put this here, 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 or here. So it can rotate 4 times. 1, 2, 3. Oh, it can rotate 4 times. But that's really weird. A circle where rotations of the same arrangement are considered distinct. Would moving it this way be the same as moving it this way? If 1, 5, 1, 5, 3, this is 2. So moving that one way counterclockwise will give us this. Or if we move it 4 times clockwise, get 1, we get 5. Oh, that makes sense. 5 actually is here though. So 1 to here, and 5 is to here. Yes, so why is this divided by 5? So something has to repeat 5 times. Maybe this can go here, this can go here, this can go here, this can go here. No matter which way we rotate them, they going counterclockwise doesn't matter. So let's try to just do it with 3 balls, and we'll draw every case scenario. So maybe that'll help. So we have the possibility of this being A, B, C. Let's draw another case. So there are in total 2 ways to arrange this. So what if we have A, B, C, and another one A, B, C. So these are all considered the same. There's 3 rotation. Oh, wait. There's only 2 different ones, so I don't understand why. Oh, I think I see what's going on. So no matter where we place the ball, the position has to be fixed when there's no rotation. So given, let's just say 4, no matter which way we rotate it, if it's rotated this way or here, no matter what, everything else has to be the same. So essentially what happens is that A has to be fixed at one of these circles. It cannot have four different positions, because any of these four different positions will be a rotation. So upon A, B, C, D, in this case, A is already fixed, so there's only one place to put it. B, on the other hand, can be here, here, or here, because these rotations don't matter. So that will be 3 times 2 times 1, and that is n minus 1 factorial. That makes a lot of sense. So just to keep this as a note, what I will draw is A here, and then we can like put a pin there. So this will remind us that considering rotation, it doesn't matter, A is fixed. At least that's how I interpret this. Not hope it's right. Alright, point number 3. The number of ways arranging n objects in a circle where rotations of the same arrangement aren't considered distinct and reflections of the same arrangement aren't considered distinct. I hope this is just, like, to me this seems fairly standard. Reflecting A gives a hold on 1 second. A here, C, and I think these stay the same. Would that make sense? Yeah, so this D doesn't rotate to here. This D wait a second. Wait, it does rotate there. Hold on, that's kind of confusing. Oh no, it doesn't. No. Rotating this way causes 90 degrees, causes D to be here. So D should be here, but that's B. So this is a different scenario. So this kind of makes sense. For every given reflection, there's only two ways to express that reflection. Even if there are multiple nodes in the circle, or whatever you would like to call them, no matter what, there's only two ways that they're reflected. And that's why, considering A is fixed here, 3 times 2 times 1, 4 times 3, and divided by 4, my bad. 1 times 2 times 2 times 1, and then we have to basically search for every case where they're the same. A only has one possible reflection here. If this was B, there would only be one possible reflection. So that means there's always two duplicates in a given n minus 1 factorial. So we just divide this by 2. So n minus 1 factorial divided by 2. That makes a lot of sense. Yes. So, as a reminder, I'll just put 1 second. I'll put it in blue to make it easier. Actually, multiple colors. So red goes here, green goes here, yellow goes here, blue goes here. So we're just saying two duplicates per letter. So no matter what we start with, because like since there's no since the rotations are distinct, basically for every letter it's also reflective of the pinned letter A. So that's what I would assume. All right, permutations. So definition of 1.2.1 states that a permutation is a possible arrangement of objects in a set where the order of objects matter. So theorem 1.2.2, number of ways to arrange k objects that have been total. Yeah, this makes sense. So if I am choosing, permutating 5, 3, 5 factorial over 3 factorial, that would give me 20, since it will be cancel out and just be 5 times 4, so that makes sense. So let's read the remark. Usually the words permute, order doesn't matter, etc. imply permutation, while the words choose, select, order doesn't matter imply combination. So let's do this problem. Peter is packing his pencil case for the AMC12. He must pack 3 distinct pencils, 2 distinct erasers, and 2 distinct markers in some order. However, he will not put an item in his case if there are already more of that type of item than any other type of item. Example, Peter will not put another pencil in his case if there are already more pencils than markers or more pencils than erasers. How many different orders are there for Peter to put items in his case? Oh my, this does not look really good. I won't lie. So let's make a case scenario. Let's say he has 2 pencils, an eraser, and a marker, 2 markers. The only thing he can put right now is another eraser. But if it's like this, they could put either an eraser or a marker. Alright, that makes sense. So let's do this in steps. The first thing he puts in the suitcase, first thing he does, he can put either one of these, but these are different numbers. I'm not sure when we would use a case scenario, but let's just start with any of them. So we have 3 choices. The next one, we have, how many choices do we have? We have 2 choices. So let's just assume we have put P, actually let's assume we have put E and M for the lowest possible thing. what next we put has to be P, and then we do that again. Any of the three, and then any of the two, and it has to be 1. And then after that, there's only one possible thing, and that's the pencil. I want to think if there's another order. What am I missing here? We have 0, 0, 0. We put 1. We will not put this because it's bigger than any of these. So he has to put 1 here, or here. But if you put something here, you can't put something here because then it will be greater than. So he has to put something here. That is really confusing. Why is the number so big? Alright, how about we graph this. Let's say it starts with we should do all these steps. So pencil, eraser, marker. So we start with P. We have to go to E, or we have to go to M. And if we do that, this has to be E, this has to be M. So from here, we have, let me write smaller, we have P, E, M, and this we have M, and this we have E. So how many is that? So going down this line, you already have 2 M's, 2 E's, P, E, M. So this is 1 P, 1 E, 1 M, and then if M has to be E, oh my bad. So M or P, and then if this is E, this is P, this is P, this is E, and then this has to be P again, right? 1, 1, 1, so 1, 1, 1, 2, so it has to be either E or P, so E, P, E has to be P, this has to be that, and this is go to P again. Alright. So counting, this is 1, 2, 3 P's, 1, 2, alright, that makes some sense, to me at least. E, on the other hand, goes to M or P. Because this would be just the same thing. If it's P, then it would have to be E or M. If it's E, it has to be M. If it's M, it has to be E. I do not see how this can possibly have 864. Because going down only one branch, we see 1, 2, 3, 4, 5, 6. So all of this is only 6. So I do not see how that can equal 864. Unless I'm reading this question wrong. Let me read this question again. Peter is packing his pencil case. He must pack 3 distinct pencils with 3 different pencils, 2 distinct erasers, and 2 distinct markers in some order. So already more than that one type of item, another type. Is there ever a situation where we're gonna have like 2, 0, 0? Does it count if it's 0? Because I guess it should. I'm very confused. Because from what's gained here, there should be only 36 ways to do it. Let me see if 36 is a multiple or like divisible into 864. Oh, it is. So 864 divided by 36, it's 24. For some reason, there are 24 other things that I'm missing. I do not see how there's 24 other branches. So 6 is here. From here, maybe another 6 here. And that would be another 6. That's 12. And then with the other 3, you get 36. But how is it multiplied by 24? Because every scenario is looked after. There should be no reason why it's not 36. I mean, yeah, 36. What are the factors? So 24, 4 times 6, that works. 8 times 3. What are these multiplied together? These multiplied together is 12. Oh, there's also 12 times 2. Maybe there's something about multiplying these together, perhaps. Oh, I see. I see. Oh, that makes sense. Yes. because the p here can change 3 times. Oh. Given what we said, this is 12, so 12 times 3 plus 12 times 2 plus 12 times 2. What would that get us? 36, 24, 48. 84. 4 times 3, 84. Is that right? Hold on. Maybe like the graph's not drawn perfectly, but in the end, it should be multiplied by 12 because there are 12 different ways for this to happen. But I'm also wondering why it's multiplied by 2. There should be no reason for that. So, what if we get... So since there's 3 ways we can put this here, that means we multiply... Yeah, we multiply the entire thing by 3, and then multiply the entire thing by 2, and then 2. I'm curious as to where the other 2 comes from, because there's no place for it. And since this graph isn't useful, let's remove the graph. So we found that there were quite a few methods to getting this PME, and then, yeah, there's just quite a few. I'm thinking maybe there's 3 ways to do the first P, but that means there's also 2 ways to do the last 2 P's. I think that might be it. So we have 3 possibilities for this P, 2 possibilities for this, and then this is just 2, and this is just 2. So I think our final formula will be 3 times 2 times 1 times 3 times 2 times 1, and that whole thing is multiplied by 3 times 2 times 2 times 2. 3 times 2, so 3 times 2 times 3 times 2 times 3 times 2 times 2 times 2. That does give 864. Oh, yes, I think that's it. So Let me just make this prettier. Yeah, so that makes a lot of sense. There's different ways to put the p here. I'm sure the actual solution might have used permutations because order does matter, the order of which the pens are placed. Yeah, so that's something to be a note of. Yeah, that looks like it makes sense. Give me a second and I will check the solution to see if that is a valid response. Well, that's my bad. I could not find the actual place where this came from, so you'll just have to assume that and take me for my word. So, yeah, this was really, really interesting because I wonder why I didn't think of that. And the 3 times 2 also, why I made it from 12 to 24. Yeah, so something to consider for future contests is that if the pencils are all different, then you can start with different pencils. You don't have to just start with the pencils, erasers, and other things. Oh, that was a pretty cool one. So word rearrangements, theorem 1.3.1. The number of ways to order a word is n factorial is the number of letters and the number of times each of the and d1, d2, d3 are the number of times each of the letters that occur more than once appear in the word. So that makes sense. It's just taking care of duplicates like we did in basically the reflection problem, where since there was 2 in every basically set, there would be you have to divide it by 2 to get rid of the duplicates. So this is what the remark 1.3.2 is talking about. Like for the circle question, that also made sense. So we have an M problem. Not sure if that means like. So in a shooting match, 8 clay targets are arranged in 2 hanging columns of 3 targets each, and 1 column of 2 targets. So that's the 2, that's the 3, that's the 3. A marksman is to break all the targets according to the following rules, alright? A marksman chooses a column from which a target is to be broken. The marksman must then break the lowest remaining target in the chosen. So the person, what I assume, is standing here, not here. He's not shooting this way, he's shooting this way. and he wants to get the lowest of whatever column he chooses until he finishes it. So let me fix this. Let me fix this guy up. If the rules are followed, how many orders can different targets, 8 targets, be broken? So keeping the formula in mind, let's see if it applies since they give us a hint. There are 8 factorial and what is D1? The number of letters, the number of times that each letter occurs. So this occurs twice. So let's do 2 factorial, which is basically equal to 2 anyways. Does that work? Let's see. 8 factorial divided by 2. Oh my god, it does not work. Let's see. I wonder how we can apply the thing that was stated earlier. So first thing, you can choose this, this, or this, so that's 3 factorial. Next, once he does that, he has, not 3 factorial, just 3. Next, he has 2 to choose from. So this is case 1 where he chooses from a 3-lined thing, and there's 2 of these, so we multiply by 2. So 3 times, next one, he can go for the same, so 3. Oh, that's a lot of case scenarios then, because even if you did eliminate this one, you can keep going here until this runs out, and you won't have a good way of doing that. So, the number of letters, obviously there's 8 ways. Is it in or in factorial? Yes. So, oh my god. 8 factorial is 40320. So, dividing the answer, we got 72. I just gave up 72 combinations. So, the discriminator has to equal to 72. I am very curious as to how there are that many duplicates. So right here we have 3 duplicates. Maybe if we do this, we have 3 more. Or if we do this, oh my bad, not 3 duplicates, 2 duplicates, 2. If we do that, we have 2. If we take another one off, it's still 2. But we can also do that here, and it will be, well, then that's nothing then. So if we do it again, it's 2, but then if we do this, it's nothing, and then we do this, nothing, 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 nothing. Oh, that is not good. Oh, so there's only 3 and 2, so there has to be a combination of 3's and 2's that multiply up to 72. So let's do the prime factorization tree to figure out what's really the problem here. 72 can be split into 36 and 2. That can be split into 2 and 18, 2 and 9, and 3 and 3. So 2, 2, 2, 3, 3. For some reason, there are 2 3's. Can I figure out? Oh, I see. So the only time there can be 2 3's is when it's here or when it's here. And the only times when it can be 2 are when it's here, here, my bad. So when it's here, here, or here, that's the only times when it can be 2. I assume it doesn't matter when these are out because because that's just a strain. That's just like a pathway. For example, you could, I don't know how to explain this, but when you do this, and when you do this, it's really hard to explain. Oh my. If you do this, and you do this, there's no other thing you can do to make. Yeah, oh, that makes sense. If you do this and you do this, there's no other way that other move between the second thing that can make these two duplicate. So you have to do this one. So that's only 2. The reason why these count is because in the middle of doing this and that, you can remove from here. So that makes a lot of sense. So yes, let me get this in color. So one here, one here. Oh my god. Let me continue it in red, and then we do yellow. So that makes a lot of sense. So, oh yes, that's how you would do this one. So that just equals to 560. Let me make that box a bit better. Oh, these are pretty hard. Let me just check if this is right. This is problem 8. Let's see the solution. Solution by oh my god, we've done it incorrectly. That solution is so genius. Oh my god. I don't know if this is right or not. I'll keep this here just in case for the future, but basically what really happened. So what they did is they arranged the left side, and since all three had to be shot, they gave each one an L, each one, each middle one, yep, they gave each middle one M, and then each right one 2. Oh, that is very smart. So there are 6 plus 2, 8 letters in total, so 8 factorial. And there are 3 duplicates of L, 3 duplicates, one second, let me switch the color. So there are 3 duplicates of L, 2 duplicates of green, and 2 duplicates, 3 duplicates of blue. And that's basically since 3, 2, oh my bad. No idea what happened. Huh. Alright, let me fix this for a second. I just won't use the colors, I'll just speed this up. So 8 factorial over 3 factorial, 2 factorial, 3 factorial, left, 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 middle, middle, right, right, right. Thinking about this, I want to see if we can do something about this problem. Let's see, so we have 3 P's, so P, P, P. Oh, right. So we have M, M, and E, E. Let's see, how many letters is that? It's 4, 6, oh my god, 7 letters. 7 factorial, 1, 2, 3, 4, 5, 6, 7, 7 factorial over 3 factorial times 2 factorial times 2 factorial. Oh, thank God, it does not work. It does not work. I wonder why though. Why does it not work? Let me see. Oh, I think it's, yes, it's once again relating back to the point that P Oh, yes. So what happens here is that they're finding ways to arrange this and it ignores duplicates. But that doesn't mean anything, because duplicates can happen here. Yeah, so that makes a lot of sense. So basically what's happening is that since we're not actually finding the order of which we shoot, oh no, my bad. So in this question, there's no specified order. He just has to break them all, and that's good. But in this place, we have conditions where things cannot be beside each other. So we can't have something like P, 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 and then E, E, M, M. That is not possible. It has to be in a specific order, P, E, M, P, E, M, P, etc. So that's why these two questions are different. Using the letters Alright, let's do AMC10. It's hopefully easier. AMOSU form 5-letter words. If these words are arranged in alphabetical order, then the word American, what would use a co, so USA Mathematical Olympiad, that occupies position. Then the word oh, I see. Occupies what? No, I do not see, apparently. What position does it occupy? I'm very, very confused. What word can we form with this? Like, mouse? Is that a word? These words are arranged in alphabetical order. These words are arranged in alphabetical order. It would make sense if it says position 3. So this would be USAMO, and then these would have their, because there's no way U can be at the front. If the words are arranged alphabetically. So I'm very confused as to what this question is asking about. I'll search it up just to see if it's worded wrong. Oh, it's problem 9. Oh, I am very confused as to what this is asking for. First 4 letters. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So this is in alphabetical order. Oh, I think I get it. Alright. I think what's being asked is if we have a list of every single possible word, SU, AMOUS. And then we continue down the list. It's asking for the position of USAMO. What would be after that? USA AMO. Oh, that wouldn't work. Next one after A is A. It would be this. US Mao. Alright, so it wants us to find here so this sounds pretty easy. For words starting with A, we have AMOUS. Would it just not be? This is required. And there's 4, 3, 2, 1. So this is just 4 factorial. And we have 4 of these. So that's the amount of numbers. And then we just have to find the numbers to U. USAMO. USA. Then A would have to be here. AUA. Oh my god. OS. UAMOS. So putting UA, there is 3 ways to arrange that. S comes last. Oh, it's not A. My bad, it's not A. That's the first one. S, the next one's O. Oh, it has to be the latest one. So O, S, M, A. Oh, that makes sense. So given each letter here, since U is last, S is last, you have 3 possibilities. So considering that, so there's 3 factorial because there's 3 positions for each of these letters, and then there's 3 combinations of them. So let's add this up. 4 factorial 24 plus 6 times 3, 8. Oh, am I doing this wrong? 24 times 4. And then 3 factorial is 6. And multiplying this by 3. So 18 plus 96, I think. And then we have our answer, 114. But the solution is 115. Oh, it's asking for the position, not the number of things before it, so I guess we also have to add 1. That makes a lot of sense. That makes a lot of sense. Alright, so let's condense this. We do not need this. We can also take this out. Let's just put some random number with M. So M, A, O, S, U. And then U, S, M, A, O. Just keep this for notes. And then the answer. So that's the final answer. Right. Combination is a possible arrangement in a collection of items where the order of selection does not matter. Let's see how long this is. Oh, but that's it. So yeah, we'll stop after combinations. So a combination is a possible arrangement in a collection of items where the order of selection does not matter. Theorem 1.4.2, the number of ways to choose k objects out of a total of n objects is choose n from k from n factorial over k. Notice that, yeah, so this is very important. I already knew this, but time and time again, it's a lot of people don't really like doing this. So considering that we're choosing 2 from 3, the formula going from here is n3, and then it's like 3 factorial, and then, oh my bad, it's 2 factorial, and then 3 minus 2 factorial. But this is a bit slow. I guess maybe you can only use it in like proofs or during algebra. However, this way is quicker. Considering 3 from 2, this is equal to 3 from n minus 1, so 3 minus 1, so it's 3. And that's very much faster. Given something like choose 11 from 9, you can instantly simplify this to choose 2 from 11, simplify that to basically just 110 over 2, which is 55. So another theorem that I don't know if it's written here or if it's implied, but how I like to do it. Oh yes, it's written right here. It's written right here. It's like given maybe like 11 and 9 again. Let's say you didn't know this, or you have maybe like 5 in the middle. Choose 11. Let's do 10. Let's do 10 and 5. No matter what, it's always, even if you subtract it, it's always 10 and 5. The way you would do this is you do 10 factorial 10 times. So 10 times 9 times 8, 5 times the number of k, which is shown here, times 7 times 6, times 5, is it? No, 10, no, you do not do the 5, my bad. You just do 5 terms, and then you divide that by 5 factorial, so 5 times 4 times 3 times 2 times 1. So what we can do, let's just simplify this. 3 times 2 times 2. this is just 9 times 7 times 4. That's dramatically simplified. We can do that. Hold on, let me write. Let's write this. So 7 times 9, that would be 63 times 4. That's 12, 252. Let's see if we get the same thing. 05 from 10. And confirming through the internet, it is indeed 252. Let's make that a bit prettier. Yeah, so this is a very important thing to keep in mind. It makes things very much faster, especially in competition. That's like one thing I need. So to recap, basically, oh, nothing is saved from up here. Whatever, it's recorded anyways. So yeah, so one thing that's really useful is this word theorem thing. And what we have to do is we have to consider everything. We have to consider scenarios where it's possible for us to rearrange the problem in words. So this works whenever the problem does not have any strict requirements and it's all in a linear order. Next we have, this is pretty standard. Yeah, it's just basically figuring out the amount of things, and if you ever have something distinct, you always factor that in. And yeah, so that will be it for today's episode. Tomorrow we will be talking about subsets, and oh, there's a lot of problems to do next time. And then we will be on probability. Alright, goodbye.